start our interview with a very brief introduction, ma'am. So can you give us some basic information about yourself?
Okay, I'm Professor Jenny McKinley. I'm based in geography in Queen's University Belfast. I'm a geologist. I studied geology many years ago. And as part of that, I did study through my time in university mathematics and statistics. But it has been since really doing my PhD that I began to really get interested in how mathematics and statistics and geostatistics was linked to geology in so many ways. But please call me Jenny. Actually, during the interview would be great. Thank you.
Okay, thank you so much, Jenny. It is really an unconventional field of study, very interdisciplinary and a very STEM-heavy field. So let us get right into the meat of this. And let me ask you, please, what is the connection between mathematics and geology?
So they are obviously two different disciplines. In fact, I would also include geoinformatics and statistics. So it isn't just mathematics and geology, but there's a whole range of different other disciplines linking with geology. But the link is that there are issues within the geosciences, geology, challenges that we face, especially in sustainable development and so many others that require a combination of mathematics, statistics, geoinformatics, remote sensing, so many other areas to come in. So mathematical geosciences or geomathematics are where those interfaces are linked. And so to address the actual challenge, we work together to do that.
Okay, so thank you very much for that. Now, if I may ask, can we go a little bit more into the detail? Like, what are some examples of specific maybe branches of geology or geosciences and specific branches of mathematics and how those overlap?
Well, I mean, in anything in terms of geology, when you think of geochemistry or geophysics, and there's, so many more medical geology, anything like that. But, if you think of geochemistry as a sort of one example, so that is obviously the study of mineralogy, understanding the elements, understanding the molecular structure and the composition of rocks. But actually, geochemical data are what we term compositional. So they're proportional and they require certain approaches to actually preserve and to respect the nature of the data. So that then brings in mathematicians and statisticians to actually work together with the geologists or the geochemists to actually develop, I suppose, solutions to address challenges so that our outputs, so we can stand over them so that they're robust. Again, in geophysics, it requires a lot of information on mathematics or physics, but that includes, mathematics is central to physics. Again, working with the geologists or the geophysics to actually find the solutions and challenges to those. So if you think about many aspects in different areas, even in mining or mineral prospecting or anything like that, it includes a simulation, so geostatistics. So again, that is statistics, but statistics taking into account the spatial location of those elements, measurements, samples. So that's the core, is not just mathematics or statistics, but it's actually recognize the importance of the spatial location, where things are. And geologists understand the importance of mapping. And therefore you bring it together, something like geoinformation systems and science with geologists, then you have much more geoinformatics. So you're bringing that understanding of the earth and the subsurface of the earth with the skills to be able to develop and analyze the materials that you might find there so that we can address the challenges and the issues that the world faces today.
When I was looking up geomathematics on the internet for the first time, or for one of the first times, I remember being shocked that one of the first areas of application was crystallography. I would have never expected it to be so intricately tied to mathematics. Can you maybe give our audience like a 2-minute explanation of what the connection is between crystallography and mathematics?
Well, if you think of crystallography or any mineral, then it has, again, the nature, the characteristics of that mineral. And any geologist will have worked through all of their different diagrams of plotting the minerals and looking at the different facets of the minerals and how they differ between each, different, quartz will differ from a feldspar, and the way that it behaves, especially through formation and then diagenesis. So all of that includes mathematics. Whether geologists realize they're actually using mathematics or statistics or not, it is integral to understanding the 3D morphology of different crystals, and that's crystallography. When we look at crystals and minerals under the microscope, again, we're looking at them in different ways. We're analyzing, their biointerference. So we're using mathematics and statistics, only we may not appreciate it as geologists. So having a grounding in that coming into a geology degree is very important. But then also, as the subject gets more and more advanced, actually working with others in that. So one thing I would stress is that a geologist is inherently, has probably the ability for mathematics and statistics, although they may not realize it. But actually, as a subject, mathematical geoscience or geomathematics means that we're actually bringing in the advanced level, we're bringing those different scientists together.
That makes sense. That was a great answer. What you were just saying prompted another question in my mind, which is, what would be hypothetically easier for a pure geologist to be able to understand that kind of math, like from scratch, assuming they haven't studied it in detail, for example, like you have, or for a mathematician to understand the geology side of the issue? So which one is harder to do?
I think this comes to the crux of the issue, in that we're not asking geologists to be mathematicians. There are some geologists who are much more, they have either studied mathematics or statistics at some stage in their degree, and they really enjoy it, or coding. Coding is becoming so much more important in geology. But there are geologists who are, field mappers. They have a really good understanding of the geology, of the development, of the progression, of the and not just the composition of the rocks, but how they have been formed. We're not saying that those geologists have to become mathematicians, but they can work with mathematicians as long as it's a two-way process. And likewise, in the mathematicians or the statisticians that we work with, we're not saying that they have to become geologists. So there's a working together. And what I would stress is that, what the IAMG and mathematical geoscience is about is, or what it's not about, and this is really important, it's not about a mathematician or a statistician saying to a geologist, give us your data, we'll do something about magical with it, produce some, wonderful output, and then we'll give it back to you, and you should understand it, and it should be perfect, because that will never work. It is about the mathematician or the statistician working with the geologist saying, this is an issue, this is a challenge. Is there any way that mathematics, computer science, statistics can help to understand and address this issue? Then it's about the mathematician and the geologist working together to try and come up with a solution that when the outputs are sort of provided, that the geologist believes and can say, yes, this makes sense. So it's a knowledge-informed approach. So, and that is, you can also interpret it. So I would really stress that it isn't about mathematicians becoming geologists, and it's not about geologists becoming mathematicians. It's about mathematicians being open to realize they don't know all the answers, but working with a geologist, we can find a solution. And it's about geologists being also open to realize there are lots of things. I have a certain understanding, I have an expertise, but combining with another discipline such as mathematics, statistics, or geoinformatics, then we can reveal so much more from the rocks or from the geochemical data that we have or the geophysical data that we have.
Thank you so much, Jenny. So to make sure I understand things well enough, we have this, so to speak, virtual table where people can come together, share information, come up with solutions. Now I'm trying to imagine the people who are actually sitting at that table. You have geologists, for example, climate scientists. I can well imagine that. And then I'm thinking about the mathematicians side of the table. I understand statisticians. I understand that statistics is important. Who else would be at that table except for the statistician?
Well, again, we have lots of mathematicians who see that mathematics has a lot to offer. So they have an understanding of the mathematics. And if we understand that the mathematics is robust, then they can apply that to the issues that a geologist might face. But we also may have computer scientists. Coding, as I say, coding is becoming so much more important, and automating a workflow where necessary is really important. So we may have people who are now more proficient in, well, we've always had machine learning experts at the table, but AI, deep learning, all of those experts are really important to bring to the table. But we mustn't do it with the absence of the geologist. So whether those are experts in field mapping and what we might call more traditional geology, or whether it's geochemistry or geophysics or any other brand or area of geology, modeling, so geological modeling, 3D modeling. We also, are involved in superficial geology, so understanding the soil, whether that's related to climate change, peat restoration or peat management, or whether it's then linked to human health. And that's one of the areas that I work with. So I would say that the table is open to anyone who sees that they may not have the whole picture and want to collaborate and talk to others and find, is there a way that we can actually listen to each other, respect each other's expertise, but appreciate that we may not have all the answers to address the issue that we face. But everybody doesn't have to be at the table at once. And sometimes it is a smaller grouping that maybe is able to work together to find a solution.
Okay, that was wonderful. So now I've understood the table, the sort of the types of problems that people can be working at, the skills that people can share, the types of knowledge that people can bring to that table. Now I would like to ask you, okay, well, where would those things be applied? What are some examples of real world solutions, real world industries where geomathematics or modeling or statistics or any of those things, those fascinating things that you have mentioned, where do they tangibly come into focus in the real world? Just some examples.
Yeah, well, there's lots of examples, and I suppose I can speak primarily from my own experience. So my PhD was looking at the heterogeneity of rock properties, and that rock property, the rocks that I was looking at were reservoir rocks. So yes, you could have had oil and gas in them, but also they were aquifers, so for hydrology. So I was interested in the spatial variability of rock characteristics, the minerals themselves, but especially the clay minerals. So what would affect the pore spaces? So modeling in that case and geostatistics was really important. So there's quite a lot of different companies who understand that it is a geologist, but also bringing in together geostatisticians to actually help to understand and model and then simulate those conditions. So we might be looking at an outcrop or well data, but then how do you implement that into a model and then run it through some simulations? So from natural resources, and that includes obviously from water to more critical minerals. So anomaly mapping, where are the critical minerals that we need for green energy? How are we going to map and then explore those in a sustainable way? But there are many other examples. One of the areas I work in is in geoforensics, so forensic geology. So again, understanding the soil properties and how those might be transferred, whether it's to a victim or a suspect in a criminal case, but it also might be in terms of the search, a search for something or someone. So the landscape, but again, understanding the soil and the geology because of that importance of transference. But it also might be environmental sort of forensics. So that might be contaminated land, and whether that's an anthropogenic source and the land need to be remediated. Again, it's the same idea of what is the spatial variability of the soil, how can we model that? And then the modeling is so that we can remediate it. So there's lots of different examples that we can use, that we can sort of explain the importance of data and understanding of the geology, whether that's deep geology or superficial geology or the interaction with anthropogenic or man, and then how we model it. And that's where the interaction comes about. And there's lots of companies, even in the environmental science field, that understands the importance of modeling, whether you call it mathematical modeling or geomathematical modeling. It takes that understanding of both.
Wow, that is really interesting. So I hope now our audience has a broad view of what geomathematics is, where it can be used. And I would like to invite you, Jenny, to please share your story. Like, how did you get into this field, and what are you focusing on now? What would you like to focus on in the future? And what would be some takeaways from your experience? Thank you.
So yeah, I've touched on it a little bit already. So I'm a geologist. I'm trained. I have a geology degree, and that was a very traditional subjects from paleontology right through to mineralogy, igneous, metamorphic, structural geology, sedimentology. For my PhD, I started to look at reservoir characterization, reservoir properties. And that's when I really started to understand the importance of geostatistics. So that was the area that I began to develop. As I mentioned before, I did study mathematics to a certain level, and also computer science. So I did have that background, but I would never have called myself a mathematician or a computer scientist in any way. But I enjoyed them to a certain degree. But I never actually made the connection between those subjects, which I sort of taken and were discrete, with geology, which is my passion, which I really enjoyed. In my PhD, when I was looking at the heterogeneity of the rock properties, and then looking at the data that I might get, and I studied I don't know how many hundreds of thin sections, and basically took information from those thin sections on mineralogy and the clay mineralogy, in particular, the porosity, the permeability of those. So when I started to try and model the porosity, permeability, the rock properties, that's when I realized that this field of geostatistics would be really important for my PhD. I went on then from my PhD to do a postdoctoral fellowship in a project that again was looking at the heterogeneity of rock properties, characterizing different types and different ages of formations. It was during this time that I became aware of the International Association of Mathematical Geosciences, and I presented some of my work at one of the conferences. And that's when I got a greater appreciation that there's just a whole field. There is a field basically of mathematical geoscience, and the expertise that I could tap into. Up to that point, I was probably trying to do it myself and trying to sort of look at papers, look at what's available online and learn that way. But that opened up the possibility to work with so many experts and others in the field. Bringing it right up to date, I've worked on many things, including COVID data and wastewater COVID data. But my, I suppose, current interests are in health and the environment. I am very interested in the geogenic, so the sources of pollutants, potentially toxic elements that might be already in our environment, and again, how they spatially variable. So they might vary per country. We know that some countries in the world have much higher levels because they are also natural resources. So on one hand, it's natural resources, on the other hand, it's potentially toxic elements, whether they are extracted and exposed to the human body through mining or other activities, or whether it's again in farming and they're naturally in the soil. So I have worked with cancer data and soil geochemistry, and also chronic kidney disease and soil geochemistry, and air pollutants. So what's in the anthropogenic, the human environment, and what's in the geogenic environment. And at the moment, I'm working on a project that is looking at healthy aging. So how do where you live affect your cognitive health, how well you actually will age. So those are some of the areas I'm working on. I'm also still working on contaminated land, and that comes into these nature-based solutions. So when we're looking at community gardens, developing people's use of green and blue spaces, we have to be very aware of what actually is in the soil. And before we say to somebody, yes, grow everything, your vegetables in your garden or in community gardens. So we do need to remember that we do have potentially toxic elements depending on where we live in the soil naturally or from anthropogenic sources.
Fascinating.
The flavor.
Fascinating. That is a lot of topics. Did you find anything that surprised you when you were looking at COVID data?
Well, again, unfortunately, it is where you live. The social deprivation data. So we looked at the socioeconomic data, and that is, linked to exposure, I suppose, and how closely, densely populated, denser housing, I suppose, opportunities, access to services, and also take up of those services. So increasing awareness. But yes, where we live is so important for so many things.
Yes, absolutely. And I can guess that might have been the same output for your cancer research, or was it something different?
Again, cancer research was looking at different types of cancer and the environmental factors. So where the different cases and the incidence of different types of cancer, and whether, there are lots of sources of cancers. But one example is lung cancer, and we know that's linked to smoking. So there are confounding factors. But I think the thing about the chronic kidney disease and likewise cancer is it is the practitioners, it's the consultants, it's the experts in health who are aware that there are certain individuals, increasing number of individuals, where they can't say, oh, this is the cause. There's an automatic, there is a natural cause, whether it's chronic kidney disease or whether it's cancers. And therefore it's what's known as unknown etiology or unknown causes. And so it's those cases that we're looking at the environmental factors. Of course, the environmental factors might also then contribute to some of the other known causes that we know for some of these disease. So it is internationally, the World Health Organization knows that this unknown etiology, the environmental factors, are important. Sometimes there's a concentration or more research is being done in terms of these unknown causes in some countries where the World Health Organization is working. But actually, in some of the other more developed countries, certainly I know across, in the UK and in Europe, that we do have those. They may not be in such high numbers, but we do have this underlying issue.
Yes, that is definitely very important work that you're doing, and I hope you can continue working on that. You mentioned the International Association of Geomathematics. I will certainly post a link in the description of this video so that people can come and see what the association is doing. Can you maybe tell us briefly what people can expect if they follow the association?
Well, I can certainly, what I hope would be something similar to my own experience, where we have an annual conference. We also have a number of journals. The IAMG, so the International Association of Mathematical Geosciences, sort of collaborate with Wiley and Elsevier to run a number of journals, and at the annual conference. So students, there are a number of different student chapters. For example, I'm just back from Freiberg in Germany, where the student chapter there invited me to give a talk. So we have a number of student chapters where I suppose an academic has encouraged through a number of whether undergraduate, master's, PhD students would get together. They are part of the IMG community, and therefore they also can avail of these travel grants and student awards. But I suppose if you were in a university and like me, you were doing something that you realize I'm sort of getting into, whether it's geostatistics, whether it's compositional data analysis, whether it's machine learning, AI, but using geology, I would encourage, I suppose, whether you're a master's student or a PhD student, to say to your supervisor, there is this IAMG conference. Our 2023 conference is in Trondheim in Norway in August. It will be too late to present your work there. Our next conference, we join in with the International Geological Congress, so it's in South Korea and Busan. But maybe the one after that is an opportunity for students to really think about, I could come along, I could present a poster maybe initially, or if they're further advanced, submit an abstract for a talk. I would hope, from my experience, is that everyone would get a very warm welcome. It is all, the IMG is about science. It's always about the science, but it's also about the people. So a student or a PhD student or a master's student, I would hope would expect to get some comments, constructive comments on their presentation, but it would never be critical. It would never be done in a critical way. The other opportunity at conferences is to meet the experts that you've probably read about and you've probably read their papers. These are very, very approachable people, and they are very keen to talk to students. So conferences are a great way. There are a number of different courses, such as compositional data analysis. There are courses that are run. Again, this is an opportunity to get together in a much smaller group. Before conferences, we run a number of short courses. Again, the group is never probably around about 10 or 12. So there's lots of opportunities to interact, bring your own data, try, ask questions. And then when you do sort of are ready to publish in an IMG journal. So I would certainly encourage people to reach out. The experts in the IMG that I know are very approachable and will try to respond as much as possible to any questions, or certainly at an event, try and give you constructive feedback on your poster or your oral presentation.
That is wonderful. I really hope there's somebody listening out there that will do so. But how about a slightly harder question? What if there are some younger people who are maybe in high school or middle school, and they are watching this video because at Earth Science Matters, we're about bringing this type of extremely valuable knowledge to a very wide audience. We encourage everybody to take a second look at these wonderful geoscience fields. So what can somebody like that do to become more knowledgeable? What kind of resources are out there? What would you recommend?
So anybody now, I suppose, that's studying, and Geology, unfortunately, is taught in fewer and fewer schools. Physical geography is taught in obviously more schools, but an understanding of our Earth processes has never been more important, I would say, for the Sustainable Development Goals. So what I would say is that, you know, I loved geology. I teach in, you know, a geography department. I also studied geography. Physical geography was, you know, was one of my key subjects. I would say if you really enjoy geography or geology, then stick at it as much as you can. In terms of developing those skills that a mathematical geoscience is all about, is, you know, see mathematics, computer science, statistics, geoinformatics, see those as underpinning in terms of geology, not separate. So if you enjoy mathematics and geography or geology, then think about doing both, or statistics or coding or computer science. You know, don't think of them as separate. Think of them as, actually, this is really important. I mean, chemistry and physics are also really important to geology. So I suppose broaden your mind to think that subjects are not separate. They actually are very useful when combined. It is really important. There's no undergraduate degree in mathematical geoscience, because I think actually we benefit from having experts in geology and also experts in mathematics or statistics. So don't be afraid to concentrate on one of the subjects, but always have an open mind about your interests, so you can combine that with other disciplines, especially in the mathematics and geoscience areas.
I can tell you how much I absolutely love what you said. It made complete sense, and it is so encouraging. I know it would have been encouraging to me if I had heard that a while back, and I really hope there's somebody out there listening who can draw encouragement from what you just said, because it is amazing. Both the fields have so much interesting and valuable knowledge to offer. But what if there's somebody out there who's doubting and maybe needs that last conclusion statement to push them over and to say, okay, I'm going to study geomathematics? Do you have like your favorite argument or your favorite reason as to why a young person should go into studying geomathematics? Because it's not widely marketed to, say, a young audience, as opposed to maybe other career fields such as, I don't know, law or business. So how would you market it?
Well, I think it would be very rare to find a course in geoinformatics is more GIS, Geographic Information Science. I suppose what we're talking about is mathematical geoscience or geomathematics. You won't find courses in that. But what I suppose I would encourage you to do, but I'd always encourage people to do what they really, really enjoy doing. So for me, geology, when I started to study it, I was already looking at rocks in the field. So I remember my first fossil. I remember the joy. I think I love just looking at the different types of rocks and trying to see where the boundary between one and the other is, trying to understand the landscape. So I would encourage people to get out and to really look at the landscape around them, but not just, I mean, it's beautiful landscape, but also to think about, well, how might this have been formed? But even when you're thinking about that, you know, immediately you're thinking about faults potentially, you know, why is the boundary between one and the other so discrete? And immediately that brings in, you know, the idea of some sort of statistics or mathematics. You know, to understand that, you actually have to start thinking about, well, the physics of how it was formed. So I think inherent in geology and physical geography, I would say that there is a understanding of mathematics or statistics or the underlying geoinformatics. But I suppose my final sort of parting on that, I suppose, Victoria, is do what you really enjoy, but remember that subjects are not as discrete as you might think. You know, they're not like subjects where there's a bell rings and you go to the next class. Actually, you know, sort of take that learning from one class and apply it in another. And it'll just open up so much more of your understanding and your enjoyment, I would say, of a subject.
All right, absolutely. We have a question about AI, so artificial intelligence. So the questioner is asking, I'm not sure if it was mentioned, but I was curious, how does AI come into the field? And is this seen as a positive or a challenge to the field?
So I think there's been a lot of information, a lot of news on artificial intelligence or AI. I suppose in the field of mathematical geoscience, we've always had colleagues who have studied machine learning. So the use of computers, the use of automated systems, the use of machine learning is not new to the field of geoinformatics or mathematical geoscience. And we welcome, I work with colleagues who use machine learning. So it's not seen as a challenge in any way. It goes back to one of the points I made earlier. If we throw a whole bunch of rocks or data from rocks into an AI algorithm or whatever, we can't expect an understandable result to come out. Yes, result, because a geologist hasn't been included in that algorithm, if you like. So AI looks at it, it looks for patterns, and it'll produce an output. That output might look something intelligent, or it might be completely like, a geologist would look at and go, but that's just not possible. So yes, AI is to be welcomed. But the other thing that AI does not automatically take into account is the spatial relationship between information. It's just one variable. Mm-hmm. That's I suppose the current work and the new advances. So the next stage, I would say it's already happening. But the next important thing is to bring the AI specialists, the deep learning specialists together with the geologists, the people that understand, the geostatisticians, the people that understand the importance of space, where things are, understand the connectivity. So, the law of spatial dependence in geology says that, for a continuous process, you expect things closer together to be more similar than those further apart. So if AI doesn't take that into account, then how can we expect the output to take it into account? And how can we expect the output to obey those laws, that law of spatial dependence? So AI is to be welcomed, but it is not the only answer. It is not the answer to automating our understanding of geology. So we need to work together, and it goes back to my sort of original point. It isn't about somebody taking the data, throwing it into something, or somebody handing over the data. It's about the different disciplines working together, and it's essentially and very importantly, remembering the importance of spatial location, spatial dependence. Geostatistics understands that. So we've got to make sure that we combine that geostatistics, and if we're working with geochemistry data, that compositional data analysis with any machine learning or AI algorithms. And then we'll have something really, really important. And I should say that deep learning, is something to be welcomed. There's lots of processes. We're becoming so data rich, worldwide, that we don't have time and the resources to do all of the analyzing of that. And even to look at all the resources that have gone before that possibly haven't even been digitized yet. So deep learning is to be welcomed, but it's got to be brought together with the people who understand, so that the outputs, the solution is something that we can say, yes, that could be interpreted. We can stand over that. That is robust.
Mm-hmm. Yes, I would not trust a blind algorithm to give me an accurate prediction when it comes to, well, I understand people who would say to any field, but especially in geosciences, where you have just so many unpredictabilities. But I'm not an expert, and this is why we have invited you, Miss Jenny. So thank you so much for coming on today. Since we do not have any questions, we will probably wrap up our interview, and I want to thank you again for coming. It means a lot to me personally, and it means a lot to the Geo Insider project. Thank you so much.
Thank you. Thank you for having me.